Good morning. I'm Kate Tallman coming to you from the Poker Flat Research Range. I'm an undergraduate student here at UAF, and I'm happy to be here to broadcast during tonight's countdown for the Super Soaker launch. With me is Dr. Don Hampton, the Optics Science Manager for the range and a research professor at UAF. We're in day 11 of the launch window for the Super Soaker experiment under Dr. Irfan Azeem from ASTRA, Atmospheric and Space Technology Research Associates. The launch window began at 2 a.m. and is going to run until 7 a.m. Alaska Standard Time. Before we get into the details of the launch, I'd like to mention that this broadcast is funded through a cooperative agreement with NASA Goddard Space Flight Center and their Space Science Education Consortium. This year, we have an SMS messaging system that will alert subscribers when the countdown drops and a launch is about to occur. You can sign up by texting PFRR launches to 33222.
I just got mine.
You may receive a text alerting you to the launch status very shortly before the launch occurs. This text will include a link to the live stream on the Poker Flat RR YouTube channel. For those of you in the Fairbanks area, you should be able to watch the launches from outdoors if you look northeast of town towards Chattanooga. There may be a 30-second or more delay in the live stream and the SMS messaging, so when you hear the countdown drop below 3 minutes, you should already be outside. Tonight's launch is complicated and a little unusual, so we asked Dr. Azeem to describe his experiment for us.
My name is Irfan Azeem. I'm the Chief Engineer at Atmospheric and Space Technology Research Associate in Boulder, Colorado. The Super Soaker team consists of myself and then faculty members from University of Alaska Fairbanks, from Clemson University, and from Utah State University. And the teams from these universities, University of Alaska, Clemson, and Utah State all have graduate students involved in this project, and we certainly appreciate their dedication and their hard work on this project.
My name is Patty Lynn McLaughlin. I'm a master's student at Utah State University in Logan, Utah, working in the Center for Atmospheric and Space Sciences. I'm here in Fairbanks, Alaska, working with my advisor on the Super Soaker mission, and I'm really excited to be here.
The overall objective of this experiment is to see if we deposit large quantities of water in the upper mesosphere, about 50 miles above the surface of Earth, how it impacts the local atmosphere, how it impacts the temperature of the upper atmosphere, how it impacts the dynamics, how things are moving in the upper atmosphere by the sheer presence of the large quantities of water.
A polar mesospheric cloud, or a noctilucent cloud, is when there are ice particles in the air around the mesosphere region, and the sun hits them at just the right angle, and they appear to be glowing. And so there's two names for them, because originally, when we viewed them from the ground, they were called noctilucent clouds, right? And then satellites would observe them from up high, and they would call them polar mesospheric clouds. And we didn't know that they were the same thing until, I don't know when. Sometime a scientist figured out it was the same thing. And so that's why there's like two names for them.
What we're trying to study is, can space traffic or increase in space traffic can contribute to the increased observation of these noctilucent clouds. So we have 3 rocket launches, and we are targeting to launch the rockets during the morning twilight. So the first 2 rockets will carry the TMA payload, and then the final 3rd rocket will carry the water canister, which we will explode when the rocket reaches 85 kilometers, 50 miles above the surface. So the first rocket we plan on launching around 7:30 in the morning. The second rocket with the TMA payload we will launch around 8 o'clock, and 90 seconds later we'll launch the third and final rocket with the water payload. So TMA stands for trimethyl aluminum. It's a chemical that ignites when it's exposed to oxygen. So and it's completely benign, so there are no health hazards if you're afraid about that. So we will release this TMA, or start releasing TMA, around 75 kilometers above the surface, and then we'll continue to release TMA up to 150 kilometers. So when it's exposed to oxygen in the atmosphere, it will sort of start to burn or glow, and then we'll use ground instruments or ground cameras to track how this TMA trail is being moved by the wind in the upper atmosphere. And by utilizing multiple camera sites, one can deduce how fast these winds are in the upper atmosphere are moving and what direction they're moving. We are utilizing a NASA-provided aircraft, and that aircraft will carry a camera to track the TMA, trimethyl aluminum trails. So we'll have a camera site here set up at Poker Flat, and then we'll have another site at Coalfoot, and another set of cameras will be flying on the NASA aircraft. And the reason why we're using the NASA aircraft is because we need 2 camera sites. So if the weather conditions in Coalfoot is not favorable for viewing, we at least will have a NASA aircraft with cameras, and that will allow us to use cameras on the aircraft and at Poker Flat to track the TMA trails and get our science results that we want.
During launch, I will be operating a camera here at UAF in the LV building, well, actually on top of the LV building. And the camera is an intensified infrared camera, and we're just hoping to see the noctilucent cloud form with this camera. It's just another source of data.
So there are some set of conditions we needed for our mission. That is clear sky conditions, because we're using multiple optical instruments on the ground, and we would like to have clear sky conditions so we can look at the upper atmosphere. Our success, or our minimum success criteria, is that we are able to release water in the upper atmosphere and able to see the impact of that water release on the temperature of the upper atmosphere. So if we can see the signature in some of the infrared cameras and the Lidar measurement, we'll consider that our mission was successful, and we are going to be able to provide some new scientific insights into noctilucent cloud creation.
By participating in this experiment, I'm getting a firsthand account of how questions are approached. So you don't really, you read a scientific paper about an experiment that happened, and you see the results and you see what the experiment did, but you don't get to see the process about how people thought about answering the question that they're asking, right? And there's science is so amazing because, like, this sounds a little bit ridiculous, right? That the U.S. government is funding a rocket to explode a bunch of water into the air. Like, on the surface, it sounds kind of like a waste of money, right? But it's not. And deep down, there's a lot of cool science questions that are being asked, and it'll tell us about the dynamics in that region of the atmosphere. And it is really important work. But these really complex questions can sometimes be answered by a somewhat simple experiment. And I think it's cool to see how those are designed and how it's pulled off. Like, this is amazing. There are like 20 people here from NASA to make sure this project goes off smoothly. And the scope of planning and design is just unfathomable. It takes so many people to do this kind of experiment. And everyone is so excited to be here. Like, they're all working towards a goal, and it's cool to be a part of that.
This is the first time anybody has tried to create a noctilucent cloud artificially. And if everything goes according to plan, and if we create a large, dense cloud of water, one expect to see these noctilucent clouds by naked eye. But we don't know until we actually do the experiment, because this is the first time we are doing this experiment.
So a polar mesosphere cloud can sometimes look like, in Harry Potter when he's learning to make a Patronus, and his little wand is just like little wisps of like this airy, bright smoke. That's what it's going to kind of look like in the sky. It's going to be like wispy and thin and glowing. So keep an eye out.
Okay, so as you just heard, Dr. Azeem explained that you get a 3-for-1 sale tonight. We get 3 rockets for the price of 1. We just got word from the PI, Dr. Azeem, that there's an aircraft that we need to have in place for these launches as well. It sounds like that's going to take about 30 minutes. So we'll tell you a little bit about what you're expecting to see tonight, maybe take a little break and then come back about 10 minutes before the first launch again. So as you heard, there are going to be 3 launches. The first launch is a chemical release in order to measure the neutral winds in the region where they're going to release this water. And so the stuff they release is called trimethyl aluminum. If you had a cup of it here on the table, it would actually catch on fire.
Oh,
so
wow.
it's very reactive. But when you release it at these altitudes the rocket's going to be at, it actually glows. And so it's a nice way to observe the atmosphere, and you can watch it move because you release it where the rocket goes, and then you watch it move around, and you can see what the neutral atmosphere is doing at these high altitudes. So it's a way of remote sensing winds at these altitudes. And so you need ground observers in order to take pictures of those, and ideally you need certainly more than 2, or you at least need 2 observers on the ground or somewhere where they can see those. So Poker Flat is very clear tonight. That's good. And then the second site we know, or we expect to be clear, will be the airplane, which is flying out. It'll have several cameras on board. And then our third site is the town of Coldfoot, which is just south of the Brooks Range. And we're getting word that it was cloudy before, but it may be clearing up a little bit. So we might actually have all 3 sites. So anyway, so that the reason we have to wait for the plane is we want to make sure it's in position and ready to go, and make sure they've got clear seeing conditions before they'll decide for the launch. So talk a little about what we're going to see. The timing of this, I don't remember what he explained in the video. We'll have this first TMA launch, and then about 30 minutes later they'll launch another TMA rocket to do essentially the same thing. And then about 90 seconds after that one goes off, they'll launch the one with the 50 gallons of water. And that will go up to about 85 kilometers, and it will explode at that altitude. And I think we have a little video clip we could show of the water. We'll do that in just a second. As I explained, the whole idea here is to create one of these what's called polar mesospheric clouds or noctilucent clouds. And it's called noctilucent because originally, here's the video. And so here is the payload, and this is a high-speed video, and it's going to be quite an explosion, isn't it? And this is on the ground at Wallops Island, Virginia, where the rocket team comes from. This is one of their tests out there. You can see when that goes off, what they want to do is they want to get the water out as fast as they can, and it'll be under high pressure essentially when it gets into high altitudes. And when it comes out, it should vaporize and turn into essentially water vapor at those altitudes. But when they release that, they expect it to essentially atomize, turn into water vapor, and likely to freeze and turn into these polar noctilucent clouds. So we're expecting that to happen. So what you'll be hearing, and you may have heard it already a little bit, you'll be hearing our voices as we talk over some of the video we'll be watching. We'll watch the launch from a camera pointing at the launch, and then we'll actually watch it in an all-sky camera as it goes off. And then we've got a sort of a little camera pointing where we expect for the release to happen, so we should be able to see the TMA and hopefully the explosion in that as well. But while we're talking over that, you might also hear in the background some voices coming over. That's called the range net, and that is people talking back and forth who are operating the rocket, making sure that the rocket is safe to go off and counting down. In fact, you'll hear Kathy counting backwards from 10 down to 0, and that's when the rocket will go off. So we should, about 10 minutes before the launch, we'll probably come back on and start up again, tell you a little bit more about what's coming up. And then after the first rocket, we'll watch the TMA for a while, and we'll go over a bit more about the science that's going to happen. And then we'll get to watch the last 2 rockets, and hopefully we get to see we get to see the water go off. It'd be pretty exciting. So one thing that's also going on right now is we've got several instruments on the ground supporting this. Not only will we have the cameras looking at the TMA and the release, we've got several specialized cameras. There's an infrared camera that's looking at some of the temperature and dynamics of the upper atmosphere where this release is going to happen. And we also have a Lidar system going right now that's also measuring temperature and dynamics in the upper atmosphere at the same altitude. The Lidar is, as you'll see in this clip we're going to show in just a second, is it's like radar where you send out a radio wave and you reflect something off of an object, say a rocket or whatever. In this case, you send a pulse of light, a very high power laser, and it reflects a little bit of light. And from that, you can determine density of particles up there, and they can actually measure temperature, and they can look at the dynamics up there and see that there's turbulence going on or there's not turbulence going on, whatever. So let's hear about the Lidar from Dr. Richard Collins from the University of Alaska.
I am a first-year grad student here at UAF, and I'm majoring in atmospheric sciences, and I do research here at the Lidar lab. Right now we're located in the Lidar research lab at Poker Flat Research Range in Chattanooga, Alaska.
So we use lasers to make measurements of the sky like optical weather balloons. We shoot laser beams up into the sky, collect the reflections in telescopes coming back, and use those reflections to determine the structure of the atmosphere. So the laser fires 20 times a second. So there's a slight flicker, and it can do a weird thing with your camera. Some people with their eye are more sensitive than others. The whole idea of it firing at 20 times a second is we're sending out pulses. We know when the laser fires. We have echoes from the sky coming back. We know the time of those echoes coming back. When the laser fires initially, we capture the echoes immediately, and that's the lowest part of the atmosphere. Then we wait for another time step and get the next part of the atmosphere and the next part of the atmosphere, and so on. So we onion peel the atmosphere with height after the laser fires, looking at echoes that are coming from further and further away in time. Then the laser fires again, we onion peel again, and that's how we make an optical weather balloon. So we fire the laser, we beam expand the laser so the beam becomes broad, and then we have a set of mirrors in the building that carry and direct the laser beam to the telescope that's looking into the sky. And so we zigzag through the building to where the telescope is and then send the beam out to the sky, co-aligned with the telescope so the telescope can see the reflections.
What I find interesting about LiDAR is that it's kind of like we are communicating with the atmosphere. We send out signals and receive signals in return, and from those we gain an understanding about that layer of the atmosphere.
So there's an introduction to what LiDARs are and why they're being used for this rocket as well. And we've got several other instruments. We've got ground-based cameras. They're quite interested in where the aurora is, if there's any aurora going on. There's an issue. They don't want too much aurora in this case because if there's aurora, it makes it hard for them to see both the TMA trails, and they also would not likely be able to see the cloud that they hope to form. Yeah. So in this case, it gets kind of funny. Usually at Poker Flat, we're excited to see aurora during the night. Tonight we saw a little bit of aurora, and they were a little bit nervous about that. It's kind of died down now, so I think we're fine with that. We've also got there's a radar system here at Poker Flat called the Incoherent Scatter Radar. It's measuring winds and the ion density at altitudes about the same altitudes as where the cloud's going to be as well. So
Okay.
we've got several instruments watching the same region. So it's a big collaborative effort. It's not just the rockets going up. kind of gotten away from just doing rockets. Now we have a lot of instruments watching the same place in the sky. I think we've got a little graphic here that shows different altitudes, and that we're talking about these different levels of the atmosphere, and so it's probably important to let you see what's going on. So we live down here at the very bottom in the troposphere, and that goes up to about 11 kilometers, about 6 or 7 miles up. And then we get to what's called the stratosphere. You probably heard about stratosphere, and that's kind of where the edge of where those the jet stream kind of happens, is the bottom of the stratosphere. The next layer is called the mesosphere, and sometimes it's called the ignorosphere too, because it's very hard to measure things there. Usually, when you fly a rocket, it goes right through. In this case, we're actually going to release something in there, but usually the rockets go right through, and you can't quite get to it with a balloon. So it's really hard to measure unless you've got specialized instrumentation, or in this case, do a special kind of rocket. And then above that's what's called the thermosphere. And what's interesting about these different altitudes is the thermosphere and the stratosphere. As you go higher, the temperature usually gets higher, whereas the troposphere and the mesosphere, they actually do the opposite. As you go to higher altitudes in those regions, the temperature actually goes down. So these boundaries between these layers are very important. And what we're going to do is we're going to release this water vapor at what's called the mesopause, which is kind of the boundary between the mesosphere and the troposphere, and then the thermosphere. And that's the coldest region, that's the coldest point in that region of the atmosphere, and that's usually where these noctilucent clouds or these polar mesospheric clouds form. So they're trying to really hit that sweet spot of a very cold layer to do that. So we talked about these clouds, and we call them polar mesospheric. That's because they happen in the mesosphere. But we also call them noctilucent clouds, and we call them noctilucent clouds because they were first discovered by people who were taking pictures after the sun had gone well down. They were seeing reflected light off of these clouds, and so I think we've got a graphic of that. Here's a picture from, I believe this is Florida, if I remember correctly, after a launch of a rocket, and what you're seeing is that the sun is well down. The sun's into astronomical twilight, which means it's 9 or 10 degrees below the horizon. Actually, it's 12 degrees below the horizon. But you're actually still seeing light reflected off of these clouds. And so people could figure, they could calculate that, and they could figure out that these clouds must be way up there. And in fact, they're 85 kilometers or about 50 miles up. So if you turned your car on its back bumper, and drove 50 miles an hour for an hour, you'd just be getting to those clouds. So they're way up there. So this cloud is actually formed by a rocket taking off, and I believe Dr. Azeem talked about the fact that we're probably seeing more of these clouds now because we're launching more rockets, and they're leaving more water vapor in the upper atmosphere and seeing those.
I see. And
so,
these clouds are more commonly spotted during the summer months? Is that right?
Yeah, typically, and toward the end of the summer, because that's when that temperature minimum in that mesopause is happening. You actually get colder up there in the summertime versus the wintertime. It's a little bit warmer. So very often you see them in sort of August, September time frame. A lot of people come up to do polar mesospheric cloud studies in that time frame.
Okay.
That's right. So I think we just had another update there. We're kind of waiting for the plane to get in position. What we'll do is probably take a break now and come back in about 10 minutes and hear where the plane is, and then hear from the science team whether they think it's a go for the launch. And like I said, if we get one launch, we're going to get 3 launches for one. So thanks, and stay tuned, and we'll talk to you in a few minutes.
Science to MM.
Science, were you calling somebody?
MM.
MM, you listening?
This is MM.
We like to pick up the count at 1320 UT. 420.
420?
Yes.
Copy. OC, copy?
OC copies. Science is OC on 2.
This is Science.
Okay, the Weather Service says that there's some high clouds possibly coming in from the east. He's still giving you a 50-50 chance of being clear for the next hour. The lower level clouds are splitting and going around on the terrain, but the ones that are coming in are a little bit higher, so the terrain probably won't affect them.
Copy that. Thank you.
I'd like station checks on channel 2, please. RCV,
RCV, go.
RDT,
RDT, go.
radar.
Radar, go.
Surveillances go, LO,
LOs, go.
TM,
TMs, go.
PLC,
PLCs, go.
Science,
No, go.
MM,
MM, go.
CM,
TM is go.
RSO,
RSOs, go.
the ranges go.
Science to OC.
Go ahead.
Did you copy that? I said no go.
Negative, I did not. We will be holding at 10 until we hear from you.
Copy that.
Hi, if you're just joining us, my name is Kate Tallman, and I'm coming to you live from the Poker Flat Research Range. We're here at a pause because we're still waiting on a report to see if conditions are good enough for launch. Is that correct?
That's right, that's right. So one thing that's different about this launch is there are really no onboard instruments on the rockets. A lot of the rockets we launched will have onboard instruments taking measurements for roar or whatever they're going to measure.
Sure.
In this case, they don't have that. So we really rely on the ground-based instruments, and in this case, a ground-based and airplane-based instruments to be able to do the measurements they want to get done. So they're quite worried about the weather conditions coming up. Because of the delay between the first rocket and the second two rockets, about 30 minutes, they're really worried that they'll launch the first rocket and 20 minutes later some clouds will roll and they won't be able to see that. So they're taking a good hard look at the weather forecast. They're calling National Weather Service right now to see what's going on. So we're wanted to let people know that's why we're waiting to see what the weather's going to do, and they're looking at what might happen tomorrow as far as weather as well. Okay. We also wanted to mention to people we're sort of streaming the stream here. And if the rocket does go off, just be aware that there's about a 2-minute delay right now on some of the streaming services we have here. So if you hear that we're about 2 minutes away, you might want to go outside and look right then because you might miss it otherwise. But you get 3 chances tonight. Like I said, we've got 3 rockets on the rail tonight. We launch one. If we launch one, it'll be pretty soon, and then about 30 minutes later, we'll launch 2 more at about a 90-second separation between them. Also wanted to mention, I talked about the trimethyl aluminum. That's what the first rocket's going to be. Once it's released in the atmosphere, it's quite safe. It basically oxidizes and dissipates, and it's not a problem for anybody. We've been doing these for quite a long time, and they're quite safe.
I just wanted to take a moment to remind our viewers, because of the stream, the longer we're running here, you want to make sure and refresh your browser, because you can end up getting a lag, especially if they decide that they are going to move forward with the launch. As we get closer to launch time, you want to make sure you're as up to date as possible. Now, Don, you said there's no instruments on this rocket. Is that why they are not planning on retrieving this rocket, whereas normally they do try to reuse the rockets?
Yeah, so if they've got specialized instruments on board, then they will actually use a parachute system to bring it down nice and softly, and then the next day they will go out and try to locate the rocket. They may not retrieve it that day, but they'll try to locate the rocket, get a good position, and then either the spring or even wait until the summer and go out. Well, actually, if they need to retrieve the instrument, they'll try to go out right away and retrieve the instrument. So they'll take out a helicopter and sling it out to an airport where they can put it on a bigger airplane and bring it out. But yeah, for the ones with no instruments on board, like these, there's no parachute whatsoever, and they come right down, and they're kind of flat when they hit the ground. But Poker Flat now has a clean range policy, so we do try to find every single piece of rocket that we launch, and during the summer we'll have a team that goes out and finds the parts of the rockets, and we'll try to get them back to Poker Flat, so we're not leaving parts of rockets across northern Alaska.
Now, there's also a reward system, correct?
That's right. So if you're out hunting in the area and you come across a part of a rocket and you can give us the coordinates for that, bring it back to Poker Flat, and we can verify that, we'll send you a check. And I think the number now is $1,200 for a full-size rocket and $500 for even just parts like a door or bits and pieces.
Quite an incentive.
So, yeah, absolutely. So if you happen to be out near the Brooks Range, very often you'll find bits and pieces of rockets. So, yeah. So please let us know. We are trying to clean things up there, so we're not leaving bits and pieces of rocket across the state. So.
And are we able to cut to the view of the range? So just in case you're a first-time viewer or more of a layman like myself, maybe you can explain sort of what we're looking at?
Sure. So what we're doing is Poker Flat. It's called Poker Flat, but it's actually got quite a few hills. We're up on a hill looking down at the launchers themselves, and what you're looking at is 3 different launchers there. Off to the left, there's a lit area, and you can sort of see some smoke rising up there, and there's a sort of a tall, straight thing there, and that's one of the rockets. In the middle, there's a bright light, and there's a rocket behind that bright light, and off to the right, you can see a tall, straight structure, and that's the 3rd rocket there. So that's the first 3 pads. the launch pads, and that's where the 3 rockets are sitting. It's kind of a good story. We're here in Alaska, and Alaska does get kind of cold, right? So, now all the rockets we have are solid fuel motors, and they sit inside of metal casings, and the rocket motor, the fuel and the casings expand and contract at different rates. And so if you get the casing really cold, maybe colder than the rocket fuel, it can put stress on the rocket fuel and could actually crack the rocket fuel.
Wow.
And so they really need to maintain the rockets at a certain temperature, over a certain temperature range. Otherwise, they might crack when they ignite them, and then they get pieces of the nozzle. And I like to say the thrust becomes more random at that point. It doesn't go the direction it wants to go. So the last thing we do before we put the rockets ready to go is put a really ugly styrofoam box around the rocket. So what you're seeing there on the one on the right is
high-tech warming system.
High-tech warming system, and we put a heater in the bottom of that to maintain the rocket at a certain temperature. So.
How high are these rockets going on?
So the 3 rockets, the question was how high these rockets are going to go. The TMA rockets go up to about 150 to 200 kilometers, so that's about 100 or about 120, 130 miles or so. The one with the water, they're going to release that at about 85 kilometers. I'm not sure if that's the apogee or not, but that's where they're going to release the water. So it'll go up to about 50 to 60 miles before it comes down. These are kind of lower rockets than other ones. A lot of times we'll have rockets that go to 300, 400 kilometers when we're studying the aurora, because we actually want to fly over the top of the aurora and measure the particles coming down to create the aurora. So these are some 2-stage rockets, and that's a pretty typical, or maybe a little bit lower than the normal rocket we do for our aurora.
Now, if we are able to get a launch and they detonate the final rocket to get that cloud, how long is the window do they have? Is there an amount of time before the cloud dissipates, or is that entirely dependent on?
Well, that's sort of an unknown. I think that's one reason we're doing that, because
Okay.
we don't know how fast the water will actually sort of diffuse and become so thin you won't be able to see it anymore. So there's one constraint is we have to have the rockets have to come back down by 7 o'clock local time. That's a constraint from FAA. So that's why the window stops at 7 o'clock. But I think they're hoping as the sun comes up and keeps illuminating that layer, that we'll be able to see that cloud for quite a while. And if we're lucky, we may even be able to see what's called, there are these things called atmospheric gravity waves, where you get sort of undulations in these atmospheric layers. Sometimes you see that with clouds in the troposphere as well. You see sort of those layers of clouds rolling like that. Or we might be able to see that. A lot of times with these noctilucent clouds, you see that sort of structure, and that's a fairly common structure at these altitudes, where the viscosity of the atmosphere has become different than it is down here, and you get these sort of long wavelength waves. The wavelengths are like 30 or 40 miles across, that sort of thing. So we're hoping to maybe see some of that, and hoping to see the water for quite a while afterwards.
And just can we review for those viewers that are joining us recently, what I guess what the postulations are of Dr. Azeem's experiment? It's
right. So these clouds have been observed for quite a while. They sort of appear, I wouldn't say mysteriously, but they certainly seem to happen after rocket launches where there is water that's created by the rocket launches themselves. In this case, we're actually detonating a canister with a known amount of water, and we're going to see the size and the dynamics of what this water does after we release it. So it's kind of a controlled experiment instead of just sort of relying on what random stuff happening. And so it's a way to try and understand what are the circumstances and conditions in which these clouds will form. So it's a controlled experiment. We've got a known amount of water going in a certain place and see what happens.
And is this the first time they've been able to use the NASA aircraft to measure that as well, or the first time for Poker?
No, we've used NASA aircraft for several other ones as well. So the NASA aircraft is a nice addition because if you're here on the ground, like we're waiting for right now, we're waiting to see whether we're going to get cloud cover in a few minutes. Whereas an aircraft, you can typically fly above the clouds, so you're almost guaranteed that the airplane will be clear skies for them. But we've got the site here at Poker Flat, which has to be clear because we have multiple instruments here, these IR cameras and a few other, the Lidar we talked about earlier, need to be operating. But then we have one other site on the ground, and right now it's kind of, it sounds like it's still a little bit cloudy there, and they're not sure they would be able to use that as well. But the fact that we have Poker is clear right now, and we're hoping it will be clear for the next hour or so, and we have the aircraft, which is likely to be clear unless there's just really crazy clouds. That means that being able to measure both the TMA trails in order to look at the wind direction and speeds, and also the cloud that gets formed, we'll be able to see that from two sites and be able to do some what's called triangulation, being able to sort of measure it from two sites and figure out exactly where the parts are for those TMA trails and for the cloud itself.
Okay.
Yeah. So yeah, just to recap, we're waiting to hear back from National Weather Service. The science team and the operation team are looking carefully at what the forecast is for cloud cover, because, as we say, it's very important that they have clear skies, primarily here at Poker Flat, and make sure the airplane's in position. So we're getting that science update now.
So it looks clear now, but what we are worried about is once we launch the last rocket, we need about an hour and a half after that of clear skies. So we're discussing the conditions and looking at weather map. And then we're also checking with the pilots how long would it take them to get into position. Now they've been looping around the starting position. So we'll have another update soon if we decide to pick up the count.
Copy that. Thank you.
Okay, and as you just heard, that was the principal investigator for the mission, Dr. Azeem, talking about what they're looking at as far as weather, and they're still concerned about some possible clouds rolling in. So I think we'll stand by here and see what's going on. I think we have. I was talking about the styrofoam box around the rockets. Here's a picture of the 3 rockets on the range during the daytime. And you can see they're on the launch rails, and you don't see the rockets themselves. You see a styrofoam box around there. But again, that's to maintain the temperature for the rocket motors. And in this case, we've got 50 gallons of water, and you don't want to let it sit out there at minus 20 and freeze,
Sure.
because it wouldn't do exactly what you want to do. Then you'd have ice cloud instead of a water cloud. So I think what we might do here is take another break from commentary, because it sounds like they're going to keep monitoring the weather. And if we hear that they're going to pick up the count, we'll come back on and talk about what's about to happen.
Okay.
So.
Science DOC.
Go ahead.
We would like to pick up the count at 0500.
Copy that. Thank you. Like station checks on channel 2, please. RCV?
RCV go.
RDT?
RDT go.
Radar.
Radar go.
Surveillance is go. LO?
LO's go.
TM?
TM's go.
PLC?
PLC is go.
Science? Science? MM?
MM go.
CM?
CM is go. Waiting on science though.
RSO?
RSO's go.
The ranges go pending the science go. Science, please come up on channel 2. Science, channel 2, please.
Science, this is OC.
Yep,
This is Science.
just doing station checks. There you go.
Science is go.
Thank you. On my mark, we'll be at 10 minutes and counting for Azeem on pad 2. 3, 2, 1, mark. We're at 10 minutes and counting.
PLC check 134.
All right, if you're just joining us, my name is Kate Tallman, and I'm an undergrad here at UAF. I'm here with Dr. Don Hampton, who works at the GI Institute and is going to do some of our more technical explanations of what's happening tonight.
I hope so. So as you just heard, we just picked up the count for the first rocket for the Azeem mission, the Super Soaker mission. If you look behind us, there's actually a countdown clock, so you can see how long it will take before we go there. And we just remind people on stream that
refresh your browser.
Refresh your browser, because there's up to about a 30-minute to a minute delay. So if you wait till the last few seconds, you might have missed it if you're here in Fairbanks and want to go outside and see it. So, we're about 9 minutes away. As Kathy just said, so that's good.
And so as we're getting closer to the launch, some of the radio chatter that we're going to hear are the safety protocols as they're running through things. Is that correct?
That's right. Yeah. So we don't just come out here and kind of sit around and then just push a button. There's quite a complicated set of checklists that we have to go through to make sure everything is going to go off correctly. That's so that we don't waste the money that we spent to put together this rocket and not have it work. But it's also for safety precautions as well. One thing you might have heard is there's a couple of people who go outside, and the picture we saw just a minute ago of the rockets on the rail, those launchers are only about 50 yards away from the highway here in Alaska. And so one thing we do is we send out some roadblocks to stop traffic to go by. We ask the traffic not go by when they launch the rockets, because that would be pretty exciting. We've also got a whole system here where we're looking at the winds at different altitudes up to about, where commercial jets fly. The rockets we launch here, we don't actually guide them anywhere. They're just basically ballistic when they go off. And the winds at different altitudes will actually push them in different directions. And so we've got a whole team here that is watching what the winds are doing at different altitudes. We've got a tower that's looking at the winds, very low altitudes, and we have balloons that go off every 15 or 30 minutes looking at winds at the different altitudes, and they've got a whole computer program that puts all that information together and figures out where all the parts are going to land. The first stage comes down somewhere, and the second stage may come down somewhere, and the payload may come down somewhere else. And there's not a lot of population north of us, but there are people who live up there, and they probably would be very surprised if a rocket landed in their street. So we make sure that all of those combinations of the winds and the rocket trajectories don't land anywhere near populated place. So some of that's going on. There's a launch safety officer whose job is to make sure that all those things are being checked off correctly. The other thing is, in this case, we're not really sending information back from the instruments, but the rocket, we need to know what's going on. So there are telemetry radars and also just tracking radars that need to be able to follow the rocket. And so we're making sure that they're ready to go. And if we were recording instrument stuff, they would have recorders ready to go as well. So quite a few things have to go on before. That's why we have a 10-minute count. So we've got time to make sure all those things are working before we count down to 0.
And just a quick reminder, if you are local to Fairbanks and you wanted to go outside and watch the rockets, you probably want to head outside around the 3-minute mark, just to ensure that you can see that. And then tonight there are 3 rockets. So can you kind of run down the timeline for our launches?
So the first one will be, looks like about 6 minutes from now. With that one, we're going to, like I said, this is going to be a trimethyl aluminum, and this is a chemical that will glow in the upper atmosphere. So if you're in Fairbanks and go outside, you should actually be able to see that. It'll be about a minute after the launch. You should be able to see the clouds start coming out. And we have a camera here. We hope we'll be able to see that as well. And then the plan there is to look at the winds and these altitudes we're going to release the water, and see what the winds are doing there. And about 30 minutes later, they will start the second set of rockets going off. That'll be another TMA release about 30 minutes later, and then 90 seconds after that TMA rocket goes off, the rocket with the water will go off as well. So we're looking at 3 rockets in about 45 minutes.
Okay.
Yeah.
And I believe while we were off air, they said that they needed about an hour and a half after the detonation of the water to do all of their measurements.
That's right. So they'll want to watch how the cloud develops. It'll start as a very localized pool of water. Well, not pool of water, but a cloud of water. They want to see how it diffuses and dissipates as it goes along. So.
And then also, we're going to switch camera angles at the moment of launch from the launch pad to.
That's right. So we'll be watching close to the launch. We'll be able to see this view, but it turns out this camera is very sensitive, and so when the rocket goes off, it basically just saturates the image. So we'll have another camera that will watch the launch for the first few seconds, and then we'll go to an all-sky camera. You'll be able to see it for a while, and then we should be able to go to this camera that should be able to watch the TMA come out. We hope we've also got it aimed right so we can, and the rocket performs correctly, so we'll be able to see the water detonation. Like the movie we saw a little earlier, we should be able to see that as well. So we're about 4 minutes away. We're getting pretty excited here. You can hear the footsteps of people going outside to watch the rocket. So we're up here at the what's called Science Operations Center, which is up on top of the hill about 2 miles away from the actual launch pads. And it's nice here because you can actually go out on the railing or on the deck here and watch the launches. If you're on lower range, again, a safety thing is you have to be in the blockhouse, which is a building with very, very thick concrete walls, and it's covered with dirt, so that if anything happens to go wrong, and it hasn't for a very long time here, that those people are protected. And so anybody on lower range has to be inside that building.
Sure.
Oh, okay.
Now, when they say holding, what could that possibly be?
Sounds like we may have some traffic on the road out there. I think we can't actually we can't actually tell people they can't drive by. We don't have the authority to do that, but we do ask people not to drive by. But sometimes people need to get by. They've got an emergency or whatever. And sometimes we have airplanes going through that are medevac planes as well. And so at those things we have to wait until they're clear and everything's safe again. So again, safety is a very important thing we do out here.
I was asking science if they wanted to wait and pick it up in a whole minute or immediately pick it up. We're ready.
Say pick it up immediately.
Copy.
So they're asking specifically when they want to pick it up, if there's a specific timing thing, and it sounds like they're just ready to go when they're ready to go.
Again, if you're local, about when they pick up the clock, you will want to head outside to make sure you can see.
3, 2, 1, mark. We're at 3 minutes, 35 seconds and counting.
Okay, here we're going again. Apparently the traffic cleared.
Elevation 84.8, azimuth 5.9. Check that 151.
So you just heard the launchers. You can actually move around and aim in certain directions. And again, part of that calculation with the wind weighting, you can move the launcher direction a little bit, and based on the performance of the rocket, that gives you the best place for the rocket to go, and it gives you where you want it to be at the right time. So those are the numbers to talk about that. That's again part of the checklist that goes through as they get down to the last few minutes of the rocket count. And you'll hear things like check 168. That means the item 168 on the checklist is being checked off. People are checking the voltages and specific parameters are met before they can launch. And there are a few people there who can actually stop the launch. As you heard, because of the traffic, they could stop the launch. There's a safety officer specifically there, and if there's a problem, he will stop the launch, he or she. So we're about 2.5 minutes away from the first launch of the Super Soaker mission with Irfan Azeem as principal investigator.
And after this first launch, what does the timetable look like for that second rocket?
So nominally 30 minutes. I don't think that's a hard and fast 30 minutes. I think they will look at conditions and see where they want it to go. The only hard and fast thing for this. So you just heard the 2-minute warning there. The only hard and fast thing is they have to have the rockets down by 7 o'clock because of FAA regulations. Again, another safety thing. So we're waiting. Apparently this is going to go off of pad 2. That's the middle pad you see there. We'll go to a different camera just before the launch, be able to see the rocket go off, and then go to an all-sky view, and then about a minute after the launch, we should start seeing the trimethyl aluminum coming out, and that will show up as a glow in the sky and a sort of a thin trail left behind the rocket. From our view, it'll look sort of like a cloud because we're kind of looking right up where the trajectory of the rocket from here, because we're at the same place with the launch point.
RDT go.
They're doing final checks to make sure everybody's ready to go.
And if you're viewing from afar, you might want to take this last chance to refresh your browser.
Right.
MM go.
CM is go.
RSO's go.
Ranges go. 50.
So 50 seconds away. This is a Terrier, modified Terrier rocket, two-stage rocket. Again, it'll get to about 120, 130 kilometers.
30.
So 30 seconds. So apparently the PI is convinced himself that the weather is going to stay clear for the next 30 minutes or so, and for the hour and a half they want to observe the clouds. So, and here we go.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, plus 1, 2, 3,
radar tracking.
So we just heard the radar's tracking. That's always a good sign.
Second stage ignition.
Now we're looking at the all-sky camera there. There's the second stage going off. Looks like we launched at 14:11 or so. That's universal time. And actually what you're seeing there is sometimes the second stage or the first stage will still sort of glow after it finishes its main part, and so you're sort of seeing the glow there. And so we're about 50 seconds in. We should maybe start looking at the other camera and see maybe we can see the TMA come out. So there you can see the stars in the sky. And hopefully if we've got the rockets going the right direction, and we've got maybe we'll see some TMA come out.
TMA trigger.
Oh, there we go. So you can see sort of move to the left there. There's a white dot there that's not a star. That's actually some trimethyl aluminum, I believe.
Okay, good to open and close all valves.
So we're about a minute and 40 seconds into this launch. This launch is releasing a chemical called trimethyl aluminum, which glows in the atmosphere. You're seeing on the screen there that brighter dot. Oh, I can see it off at the top there. Yep, onto the high. But it's coming into the screen there. Now we're seeing some of the trimethyl aluminum coming into the screen. There we go. It's drifting into the screen now, so you can see that. If you're here in Fairbanks, if you went outside, you should be able to see it as well. So again, we've got an airplane in position taking pictures of that cloud. We've got cameras here at Poker Flat taking pictures of that cloud, and hopefully at Coldfoot as well. It sounded like Coldfoot was maybe clearing up a little bit. And so those three sites are being able to watch that cloud develop. And you know it's released at where the rocket flies, and we'll have a good position of that rocket. We'll have a good record of that rocket position, and then you'll watch from the cameras from the ground how that develops. And at different altitudes, it'll be going different directions. And if you figure out what that direction is, you can figure out what the wind direction is. And if you see how fast it's moving, there you can see how fast the wind was blowing up at different altitudes. It's quite interesting because this covers about 40 or 50 kilometers of altitude, and over that range you'll see quite a few different wind directions. At lower altitudes it may be going east, and at the top it may be going north or west. But now you're seeing a little bit more of the cloud. Looks like it went a little bit higher than we expected. And you can actually see it developing live here. And so the winds at these altitudes are actually pretty impressive. They can be up to 100 or 200 meters per second, which is 200 or 300 miles an hour at these altitudes. But you wouldn't have to worry too much. It wouldn't knock your house over because it's also very thin atmosphere, so there's not much in the way of force in those winds. And that's why they can move so fast, because the atmosphere is very thin up there.
So it seems like so far this first launch is successful.
So far, so good. That's the up leg, and they'll release TMA on the up leg and on the down leg as well. I think we may not be able to see the down leg, so it should be already down. I don't know if we can look at the other all sky. You might be able to see it over there.
Yeah, directly overhead.
Okay, yeah.
Yeah.
So this might actually be the down leg too. So, looks like a good launch for the first one. They should be getting good information on the winds at the altitudes we expect to release the 50 gallons or so of water in about 30 minutes or so.
And that water, the cloud, should be easily visible to anyone on the ground, correct? Anyone should be able to see it?
That's, I think that's still, I think that's a question we'll find out in a few minutes, whether it's going to be visible or not. The TMA is quite visible because it actually glows in the well, here comes the down leg. There we go. So we were seeing the up leg. Now you see the down leg, and so you can see what they do is they actually have little puffs. They turn on and off the valve that opens up, lets the TMA out, and that also helps again with the triangulation from the multiple cameras, so you can actually follow one of those little clouds around. If it was a continuous stream, it would be kind of ambiguous which part of the cloud you should look at from the two sides. But with these little puffs, you can actually figure that out. You can already see that up near the top, it's already sort of blowing to the right in this view. And now you're seeing what's called the halo that comes down afterwards. When you release on the up leg, now you're basically in space, and so what happens is some of the particles they don't essentially react right away, and so they basically follow the rocket around, and when they come back down, they spread out from the rocket. When they come back down, then they start to glow again, so you see this sort of halo effect around there. So that should be nice and bright. If you're outside watching, you should be able to see that quite well. And you see how that line is now kinked?
Mm-hmm.
So remember, that all came down as a straight line, and now it's quite kinked around. If you look from the bottom, you actually see sort of a corkscrew shape. So very often you get sort of vortices or different winds at different altitudes. It's quite obvious. So quite a bit of information from this. And we've also got a reminder that we've got the laser radar, the Lidar, is running as well. It's measuring some of the same characteristics in the same region. Earlier we could actually see the Lidar on the screen. I'm not sure we're seeing that now. But if you look on the left side, you may see a little green straight line. That's part of the Lidar beam going up and measuring sort of the same volume of atmosphere.
And how far up does the Lidar reach again?
Lidar can make the measurements, I think, with this one up to about 85 kilometers, so about 50 miles up as well. So it'll be about the same altitude as we're going to release. They're expecting it to release the water. And again, this TMA trail you're seeing is probably going from about 80 kilometers up to 120, 130 kilometers or so. So what you're seeing right now is a trimethyl aluminum cloud that was released from this first rocket from the Super Soaker mission. That launched about 7.5 minutes or almost 8 minutes ago now. And so we're watching this cloud develop. We've got an airplane in the sky. Excuse me. Observing this, as well as cameras here at Poker Flat observing this cloud. And hopefully at Coldfoot as well. I haven't heard whether Coldfoot was clear or not. And they will measure the motion of this cloud to be able to measure winds at these high altitudes.
And so does it seem like we're still on track to launch our second rocket in about 22 minutes?
As far as I understand, we should still be on track for that.
So when that second rocket launches, pretty quickly after, we're going to get the third rocket.
That's right. So So what we're doing now is with this rocket, they're looking at what the winds are prior to the release of the water. There'll be a second rocket just like this. It'll also have the trimethyl aluminum, and it'll create this glowing cloud to look at the winds. And then 90 seconds after that second rocket, they'll release the rocket, or they'll launch the rocket that will have the water release. And so it will be sort of mixed in with this TMA cloud as well. So we expect to see that as well. So we're about 20 minutes from that now. That should be going on as well.
OC, this is Science.
Go ahead.
We'd like to pick up the count for 119 at 5:38.
Copy. Pick up the count at 5:38.
CMRCV. MM, this is TM.
Go ahead.
We'd like to turn on bus and transmitter on each payload just so we can lock up the ground station.
Copy.
PLC, this is TM.
Go ahead.
Can we bring on bus and transmitter on 119? Okay, PLC, can we bring up bus and transmitter on 122?
Did you want GPS and transponder up also?
Negative. We're just trying to lock up the station. Okay, we've got good lock. We can bring both systems down.
All right, good morning. I am Kate Tallman. I'm an undergraduate here at UAF, and I'm here with Dr. Don Hampton, who is the optics science manager for the range here at Poker Flat, and a research professor at UAF.
That's correct.
And he's providing the technical commentary for this morning's launch. We're in day 11 of the launch window, which runs to January 31st. And the experiment today is being run by Dr. Irfan Azeem from ASTRA, the Atmospheric and Space Technology Research Associates. And the launch window started at 2 a.m. and will be complete by 7 a.m. Alaska Standard Time. I just wanted to bring up the fact that Poker Flats is the world's only university-owned scientific-sounding rocket range. And then also that this broadcast is funded through a cooperative agreement with the NASA Goddard Space Flight Center and their Space Science Education Consortium. Along with Dr. Azeem, he's working with co-investigators from UAF, Clemson University, the Naval Research Laboratory, and Utah State University. So it's quite a large team of people out here.
That's right. And that's pretty typical for these rocket shots. It's very rarely just a single person. It's usually a science team that comes, and it's usually a diverse science team, so from many different institutions. So we get to see lots of people. It's nice to see all of our friends come up here. So yeah, about 15 minutes ago, we launched the first rocket of 3 rockets we're expecting to launch tonight. The first one was a trimethyl aluminum release to look at the neutral winds in the upper atmosphere, about the same altitude. We're going to release about 50 gallons, or about a bathtub full of water in this region in order to try to recreate what's called polar mesospheric cloud, or sometimes called noctilucent clouds. And they're called noctilucent clouds because they're so high altitude that even when the sun has gone way down, the geometry is such that the light still shines on them up at 50 miles altitude, even though they're not shining on the clouds that we see down here in the troposphere. So these have been observed for quite a while, and there's a lot of speculation on how they're created. This is sort of the first attempt to actually do a controlled experiment on creating one. As you said, the principal investigator, the leader of this is Dr. Azeem, and he was kind enough to spend some time with some people at the GI to talk about his experiment, and I think we've got a clip here. He'll be able to explain a bit more about his experiment.
My name is Azeem. I'm the Chief Engineer at Atmospheric and Space Technology Research Associate in Boulder, Colorado. The Super Soaker team consists of myself and then faculty members from University of Alaska Fairbanks, from Clemson University, and from Utah State University. And the teams from these universities, University of Alaska, Clemson, and Utah State all have graduate students involved in this project, and we certainly appreciate their dedication and their hard work on this project.
My name is Patty Lynn McLaughlin. I'm a master's student at Utah State University in Logan, Utah, working in the Center for Atmospheric and Space Sciences. I'm here in Fairbanks, Alaska, working with my advisor on the Super Soaker mission, and I'm really excited to be here.
The overall objective of this experiment is to see if we deposit large quantities of water in the upper mesosphere about 50 miles above the surface of Earth, how it impacts the local atmosphere, how it impacts the temperature of the upper atmosphere, how it impacts the dynamics, how things are moving in the upper atmosphere by the sheer presence of the large quantities of water.
A polar mesospheric cloud, or a noctilucent cloud, is when there are ice particles in the air around the mesosphere region, and the sun hits them at just the right angle, and they appear to be glowing. And so there's two names for them, because originally, when we viewed them from the ground, they were called noctilucent clouds, right? And then satellites would observe them from up high, and they would call them polar mesospheric clouds. And we didn't know that they were the same thing until, I don't know when. Sometime a scientist figured out it was the same thing. And so that's why there's like two names for them.
What we're trying to study is, can space traffic or increase in space traffic can contribute to the increased observation of these noctilucent clouds. So we have 3 rocket launches, and we are targeting to launch the rockets during the morning twilight. So the first 2 rockets will carry the TMA payload, and then the final 3rd rocket will carry the water canister, which we will explode when the rocket reaches 85 kilometers, 50 miles above the surface. So the first rocket we plan on launching around 7:30 in the morning. The second rocket with the TMA payload we will launch around 8 o'clock, and 90 seconds later we will launch the 3rd and final rocket with the water payload.
During launch, I will be operating a camera here at UAF in the LV building, well, actually on top of the LV building. And the camera is an intensified infrared camera, and we're just hoping to see the noctilucent cloud form with this camera. It's just another source of data.
Our success, or our minimum success criteria, is that we are able to release water in the upper atmosphere and able to see the impact of that water release on the temperature of the upper atmosphere. So if we can see the signature in some of the infrared cameras and the Lidar measurement, we will consider that our mission was successful, and we are going to be able to provide some new scientific insights into noctilucent cloud creation.
By participating in this experiment, I'm getting a firsthand account of how questions are approached. So you don't really, you read a scientific paper about an experiment that happened, and you see the results and you see what the experiment did. but you don't get to see the process about how people thought about answering the question that they're asking, right? And there's science is so amazing because, like, this sounds a little bit ridiculous, right? That the U.S. government is funding a rocket to explode a bunch of water into the air. Like, on the surface, it sounds kind of like a waste of money, right? But it's not. And deep down, there's a lot of cool science questions that are being asked, and it'll tell us about the dynamics in that region of the atmosphere. And it is really important work. But these really complex questions can sometimes be answered by a somewhat simple experiment. And I think it's cool to see how those are designed and how it's pulled off. Like, this is amazing. There are like 20 people here from NASA to make sure this project goes off smoothly. And the scope of planning and design is just unfathomable. It takes so many people to do this kind of experiment. And everyone is so excited to be here. Like, they're all working towards a goal, and it's cool to be a part of that.
This is the first time anybody has tried to create a noctilucent cloud artificially. And if everything goes according to plan, and if we create a large, dense cloud of water, one expect to see these noctilucent clouds by naked eye. But we don't know until we actually do the experiment, because this is the first time we are doing this experiment.
So a polar mesospheric cloud can sometimes look like, in Harry Potter when he's learning to make a Patronus, and his little wand is just like little wisps of like this airy, bright smoke. That's what it's going to kind of look like in the sky. It's going to be like wispy and thin and glowing. So keep an eye out.
So we just heard from the operation manager that we're about to pick up the count at 10 minutes for the second and third rocket for the Super Soaker mission. So things are getting exciting. Now, Dr. Azeem and a student talked about the release that's going to happen.
Will be 10 minutes in counting. For Azeem on tag 1. 3, 2, 1, mark. For 10 minutes in counting.
And you can see on the clock behind us, you can watch the countdown. We might remind people about the timing for going outside.
At about 3 minutes, if you're local and you'd like to step outside and watch the launch, you want to head outside then to make sure you catch it. And then also, if you're streaming, if you've been streaming with us for a while, there's probably a delay happening. So especially as we get closer to the launch, you want to make sure and refresh your browser.
So we're about 9.5 minutes away. So again, just to remind you, there are going to be 2 rocket launches about 90 seconds apart. The first one will be another trimethyl aluminum launch like we just saw earlier, and we should be able to watch that come out as well. But then 90 seconds later, a second rocket is launched, and that'll have about 50 gallons of water on board. And when that gets to the right altitude, about 85 kilometers, they're going to detonate the canister and release that water fairly quickly. And we've got a video of a test they did at Wallops Island in Virginia. This is the main NASA facility for doing these sounding rockets. And you can see there the water comes out quite rapidly, and so it should dissipate into the atmosphere quite quickly. We expect we'll be able to see that. We've got a camera. We may be able to watch that live. We've certainly got multiple cameras here at Poker Flat watching this event, so they will be able to watch that. And then the thing we'll do for the next hour and a half or so, they're expecting to be able to watch this cloud as it develops. Right now it's being limited by moonlight as the morning goes along. As the sun gets closer to the horizon, the sun may actually hit the cloud as well. We'll be able to watch that in sunlight. So that's the plan. The idea is to see how this cloud develops, how quickly that water dissipates and gets entrained into the right altitude to make these polar mesospheric clouds, or does it just go away? We don't know. I mean, that's we see these clouds all the time, but we're not sure exactly of the source they're coming from. In this case, they will find out whether they can create one of these clouds. So we're about 7.5 minutes into from the launch now for the 2 rockets.
Now, so the point of this mission is to kind of determine the source of the clouds, but do the clouds then play a role beyond their existence in our atmosphere, or?
Well, so they're
Do they cause anything to happen, I guess?
I'm not sure they cause anything to happen. They are a sort of a remote sensing way to see what's happening in this level of the altitude, or excuse me, level of the atmosphere that you heard me call it earlier, the ignorosphere, because it's very hard to measure things at this altitude. So this is sort of a way of measuring what's going on. If you have the right kind of camera and take time lapse of these clouds, you can actually watch sort of the dynamics of the clouds and see whether what we call atmospheric gravity waves, which are sort of a disturbance in this middle atmosphere range that actually carries a fair amount of energy. It's one way of either cooling off or heating up the atmosphere by driving these waves from one region to another region. So it's a way of dissipating some energy in this middle atmosphere. And there's a whole groups of researchers trying to understand these. So one way they can do that is they use the Lidar, which is being operated right here at Poker Flat right now. You can watch these gravity waves happen with a Lidar, but that's basically just a single point because you've got this one Lidar or laser beam going on. The clouds, you can actually see sort of a two-dimensional effect going on. There's nothing that happens, and we don't have a good example of that here now, but there's also some chemistry that goes on in this same region, and so you get this sort of diffuse glow that happens. And another way of observing this atmospheric altitude range is looking at with very sensitive cameras to see this what's called air glow. And again, sometimes that's affected by these gravity waves as well. So all of these are sort of tools to try to understand the dynamics of this middle atmosphere. Now, this middle atmosphere is sort of the upper end of the troposphere and stratosphere, and that's what we're kind of concerned about as far as climate change and how that's going to be affecting us.
Okay. And I believe, if I remember correctly, they said the second rocket is launching from Pad 1?
I believe so, yeah.
And then the third rocket from 3?
Pad 3, yep.
Okay.
And we were talking a little bit earlier, these rockets, in this case, these are actually surplus military rockets. NASA works with the DoD, and the Department of Defense will have to change their inventory, and so NASA is able to pick these up. Now, they do a lot of very careful screening of these the rocket motors before they will put them on a pad to launch them. Again, very concerned about safety, but it also is a much lower cost method for getting these sounding rockets.
Sure, yeah.
And now the interesting thing about sounding rockets is they're very, they can be very focused science. The nice thing about rockets is you can launch them when you want to. Right. You don't have to wait for if you have a satellite going around, it's going to go over when it happens to go over. Whereas a rocket, you can launch it the time you want to launch it. And so a lot of times when we do auroral missions, we have to wait for the right auroral conditions. And if you had to wait for a satellite to come over, it's probably going to come at the wrong time. So the nice thing about rockets is we can do the same. And we can do that here. He's made the choice of when he wants to launch these rockets based on the geometry, when he's going to be able to observe them, and also when the skies are clear. So he was able to wait for that. So sounding rockets are an important tool for science, especially in this upper atmosphere and aurora range as well. So about 3.5 minutes.
So the triangulation for this particular launch is happening here, Coldfoot, and with the aid of the NASA plane, correct?
That's correct. Yeah. So they've got generally you want 3 sites if possible, but you can do the triangulation of these clouds with 2 sites. And so to help improve the probability that at least one of them will be clear or 2 of them will be clear, they decided to bring up an airplane. Because typically you can fly the plane well above the clouds and know it's going to be clear. They did have to have Poker Flat clear because we have multiple cameras and instruments on the ground to be able to observe the clouds and to do some of the primary science for that. So, So yeah, so they've it's a little bit different. We haven't had many planes for NASA launches here before, but this time they decided to bring the plane out.
Very cool.
Yeah. So we're about 2.5 minutes away from the second launch for the Super Soaker mission. And just a reminder for those who might have just joined, there are going to be 2 launches fairly close succession. There'll be 1 launch, and about 90 seconds later will be a second launch. The first one will be a trimethyl aluminum, which will be leaving a trail, a glowing trail, in order to measure the winds in the upper atmosphere. And then the second one will be the primary launch for this mission, which is about 50 gallons of water, about a bathtub full of water, released sort of dramatically at about 85 kilometers, about 50 kilometers altitude, in order to try to reproduce a polar mesospheric cloud, or what's called a noctilucent cloud as well.
And if you're local to Fairbanks and you want to see it live, you should have been outside about a minute and a half ago.
But you do get 2 chances here. And so now you're hearing the people in charge of the launch are talking about making sure all the parts are ready to go, and you're going to hear a list here of all the people who are saying they're ready to go now.
PLCs go.
Science?
Science is go.
MM?
MM go.
CM?
CM is go.
RSO?
RSO's go.
Ranges go. 60 seconds.
So a minute away. All the checks were good. So launch number 2 for Super Soaker.
40.
And pad 1, is that in the upper right?
Pad 1 is on the very far left.
Oh, okay.
Right. Correct, I should say.
30.
We'll see a little bit different view at the launch because this camera just completely saturates when it goes off.
20. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Fisheye lens that sees from horizon to horizon. So there was the first stage, and it's still glowing a little bit, and you should see the second stage kick off here in a second. There goes the second stage.
Plus 20.
Right of track. High on elevation.
And so on the ground they have radars following the rockets, and they're also quite interested in where they're going to make sure they're not going to go adrift. And we talked about earlier, they will track that rocket all the way down, and that helps them know where the rocket will be landing, so they can go and retrieve the rocket this summer.
Radar dropping track.
So, oh, there's a satellite on the left.
Plus 50.
I think that's actually a satellite. I don't think that's our rocket. Oh, no, that's the first stage. I take it back. That is our first stage coming down.
Plus 1 minute. 30 seconds and counting on pad 3.
Okay, so remember, we're going to have a second rocket here very soon as well.
207, ready.
20 seconds.
Interim launch motor enabled.
Oh,
Cloud close, stop open.
there comes the first stage down.
9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Plus 1,
There we go.
2, 3,
The third and final rocket.
9, 10.
Now you can see some of the TMA released from the first rocket on the right, and you're seeing the second rocket go up there. So lots of things going on at once. This is a very busy mission.
And this final rocket flies to a much lower altitude than
Right,
the previous
it's not going to go as high. It's maybe a little heavier, and so pretty soon I expect to see perhaps a detonation.
Stage burnout.
Plus 40.
So you're seeing the TMA cloud up at the top. That was the up leg. TMA trimethyl aluminum. It's a chemical that glows in the upper atmosphere, and we can watch how that cloud moves around. How that cloud moves around and infer what the winds are in the upper atmosphere. And then pretty soon we might be able to see here the detonation of the water canister. So we've had 3 successful launches so far. The rockets have performed nominally, it sounds like, from the noise on the range net. Oh. I think I did see a little flash on the screen there, but it was pretty brief. And they just said LOS, that means loss of signal. So I think that means that the computer on board the rocket that had the water, when it exploded, probably the computer is no longer working, so they're not getting the telemetry back from that rocket. Now they're still tracking it with their radar, and so they'll be able to track where it comes down. But the telemetry, the information coming back from that rocket is no longer coming back. And pretty soon.
I'm sorry, is that the Lidar? I see the beam.
Yes, if you see from from the sort of upper left, sort of to the middle, that's the Lidar beam. Now we should start seeing on the down leg. We shall see some more TMA being released. We should start seeing some little puffs come out.
Scientific term.
That's right. I'm seeing sort of the halo come out. Well, we're not seeing the TMA on the down leg yet.
Oh, there we go.
Oh, there it is. Okay. Just took a little time. And again, they turn on and off the valve for coming out again to make individual clouds so you can watch those clouds move around. So it looks like we've had 2 successful TMA releases, and it looks like I'm hearing some noise from the science room back there that they confirmed that they did get the release of the water. So
they're going to be watching this for the next hour and a half.
So the plan is to have the cameras observing this for the next hour and a half. And as the moonlight is on the water cloud now, and as the sun comes up, we should be able to see more. So in the other room, they've actually got some infrared cameras that should be able to see the water a little bit better than we can see with this camera here, and some other more sensitive cameras than we have as well. So we'll be looking at the water cloud that was formed. So quite an exciting night here at Poker Flat. We've had 3 launches in about 45 minutes. This is 3-for-1 sale here at Poker Flat. So now we're looking at the all-sky camera and that big halo cloud you're seeing sort of off to the north now. And now back to the sort of narrow field camera. Now you can see not only does do those clouds move around, you can also see they become kind of turbulent. And again, that's part of what they're looking at with this mission, is to look at that, understand that sort of transition from a very smooth cloud up on the top to this sort of turbulent cloud on the bottom. So this whole region of the middle atmosphere, many things change. You go from this very, very sort of smooth laminar flow up top to sort of a more turbulent, sort of chaotic flow a little bit further down. So if you happen to be here in Fairbanks, it's not a UFO outside. That's a chemical release called trimethyl aluminum. It's very benign, but it's a nice way for us to observe a range of the altitude range of the atmosphere that's very hard to measure otherwise. You can't take a balloon that high up and you The only way you can really get to it is to have a rocket release this chemical on the way through.
And for those that are local, you said as the sun comes up, there's a possibility they might be able to see the cloud
You might
itself?
be able to see the cloud. It'd probably help if you had a nice camera that could observe take pictures, sort of time-lapse pictures or long exposure to pictures of the cloud.
Probably better chance if you're not in town.
That's
Light
right.
pollution,
Yeah. So you want to be, sort of like when you go to watch the aurora, you probably want to be away from light pollution and have a nice camera that can see that. So. So I think we've had 3 successful launches here. It sounds like at least the initial requirements were met. So it looks like a successful evening or morning in this case. So I think we'll leave some of these images up here, but I think we may sign off now and let you enjoy the rest of the day.
Go ahead.
We have ice. Looks like we have a successful launch. Thanks again for all your hard work.
That's good news. Thank you.
Lidar, this is OC.
Go ahead.
I just want to confirm that we do have cloud echoes in the Lidar data, so we have success there too, as well as the visible cloud. Over.
Very good. Thank you.
Project 41122, post-flight AGC calibrations for 9-meter 1 antenna system. Receiver sets 1 and 2, link 79, frequency 2279.5 megahertz. Signal generator level at MDS is minus 69.6 dBm. Test inject loss is 46 dB. RF off. MDS. Plus 5. Plus 10. Plus 15. Plus 20. 25. 30. 35. 40. 45. 50. 45. 40. 35. 30. 25. 20. 15. 10. 5. MDS. RF off. Project 41122, post-flight AGC calibrations for 10-foot antenna system. Receiver sets 3 and 4, link 79, frequency 2279.5 megahertz. The signal generator level at MDS is minus 59.3 dBm. Test inject loss is 59.4 dB. RF off. MDS. Plus 5. Plus 10. Plus 15. Plus 20. 25.
Attention all personnel.
30.
There will be a post-mission debrief at
40.
the rack at 7
45.
a.m. Attention all personnel. For those of you that are not going to be at the debrief and are planning on leaving, we've just had a report that there is a vehicle that has rolled just past the Chattanooga Lodge. There is some emergency equipment both on its way and at the site already, so please be very cautious when you leave. Thank you. Lauren Neely, please call 2190. Lauren Neely, 2190.